Nature is inherently chaotic, full of unpredictable variables. To analyze it, especially its most dangerous microscopic elements, we must strip that chaos away. That is the core purpose of a modern laboratory. As we see in this definition, a laboratory is a facility engineered to provide rigidly controlled conditions. It is a space where scientific research, experiments, and measurements can be performed with absolute stability. Bringing dangerous biological agents into this space creates an immediate tension. We need proximity to study pathogens and toxins, but that proximity places the researcher in the direct path of the hazard. To manage this tension, laboratory architecture and operations rely on two foundational pillars: biosafety and biosecurity. While the terms overlap in common usage, they defend against distinct categories of threat, based specifically on human intent. Mastering clinical and research operations requires understanding exactly how these two frameworks lock together to form a comprehensive defensive matrix. Ultimately, a high-level laboratory operates as a fortress. It is engineered to prevent human error from letting biological hazards out, while actively keeping malicious actors from getting in. The World Health Organization defines biosafety as the containment principles, technologies, and practices implemented to prevent unintentional exposure to pathogens or their accidental release. The CDC focuses on the micro level, applying safety equipment and procedures to protect workers during active manipulation of infectious microorganisms. The core assumption of biosafety is that the scientist is well-meaning. The system is designed to provide a safety net for the inevitable realities of human error, a sudden chemical spill, or mechanical equipment failure. Biosecurity operates on the opposite assumption. It is a system built specifically to defend against bad actors, theft, and intentional harm. This requires us to categorize certain assets as valuable biological materials, or VBMs. These are materials that require strict administrative oversight and physical control to protect the population from potential harm. VBMs include active pathogens and toxins, but also vaccine strains, genetically modified organisms, and historical archival samples that could be weaponized if stolen. Because the threat is intentional theft, a biosecurity system relies on physical infrastructure: break-proof doors and windows, securely locked buildings, and documented access control logging exactly who enters rooms containing hazardous materials. The primary distinction is simple. Biosecurity uses the physical infrastructure of the building to protect the pathogens from people. Biosafety uses procedures and personal equipment to protect the people from the pathogens. Once a researcher passes through the access logs of the biosecurity perimeter, they enter the active workspace. This is where building security ends and personal biosafety begins. The primary tool for active biosafety is personal protective equipment, or PPE. As outlined here, PPE functions as a targeted physical barrier worn to minimize exposure to specific workplace hazards, whether they are chemical, radiological, or infectious. Standard laboratory operations utilize a modular PPE system. Each component is selected to defend a specific anatomical vector based on the nature of the hazard. The first major vulnerability is the cutaneous, or skin, exposure route. The body's surface area makes it highly susceptible to large volume spills, infectious droplet sprays, or corrosive chemical splashes. To mitigate this, we deploy barriers for the torso and limbs. This slide highlights the standard options: long-sleeved lab coats for basic work, heavy-duty aprons for large volume handling, and fluid-resistant gowns for high infectious risk. The lower extremities face a different set of risks: dropped sharps or heavy equipment crush injuries, and pooling biological spills mean that footwear must be completely enclosed and fluid-resistant to protect the entire foot. But the most active high-risk vector in any laboratory setting is the researcher's hands. Manual manipulation carries a dual risk. Pathogens can absorb directly through microabrasions in the skin, or they can be ingested through secondary hand-to-mouth transfer if the researcher unknowingly touches their face. Clinical gloves solve this by providing a clean, disposable, physical barrier. The nitrile surface physically separates the skin from cell cultures and infected blood, causing hazardous fluids to slide off harmlessly. Securing the torso, limbs, and hands removes the primary pathways for surface-level contamination. Skin provides a tough natural defense, but the mucous membranes of the eyes offer pathogens a direct, rapid transmission pathway straight into the bloodstream. Ocular exposure frequently stems from subtle mechanisms. unseen microsprays generated by opening vials, aerosolized splashes during pipetting, or the accumulation of ambient corrosive fumes. Protecting this vector requires specific hardware: wraparound safety spectacles for basic impact, sealed goggles for toxic fumes, or full face shields for high splash volumes. This brings up a strict operational rule: contact lenses offer zero protection. If an exposure occurs, contacts can trap hazardous chemicals directly against the cornea, severely amplifying the damage. They are prohibited when working with hazardous agents. Beyond biological and chemical threats, the sensory organs also face physical hazards. High-decibel lab machinery generating noise above 85 decibels requires targeted foam or muff barriers to prevent acoustic trauma. Securing the eyes and ears blocks the invisible ambient hazards that effortlessly bypass tactile defenses. This diagram maps our deepest biological vulnerability, the respiratory system. Inhalation pulls airborne hazards directly through the nasal cavity and down into the alveoli of the lungs, allowing them to access the cardiovascular system. Working with dusty, toxic, or infectious materials generates suspended microscopic aerosols that can linger in the laboratory air long after the work is done. To protect the airway, we have to clarify a critical distinction. As we see here, a standard surgical mask is not the same thing as a respirator. A surgical mask is primarily designed to protect the environment and other people from the wearer's respiratory droplets. It fits loosely and provides poor filtration against incoming microscopic aerosols. For true respiratory protection, workers use specialized barriers like the N95 respirator or heavy-duty cartridge masks shown here. Unlike a loose surgical mask, these respirators create a tight physical seal against the face. This forces inhaled air through a dense microscopic filtration matrix, physically trapping dangerous pathogens before they can reach the lungs. However, a respirator rarely works perfectly alone. True respiratory biosafety requires pairing PPE with primary containment equipment, like ventilated safety cabinets or chemical exhaust hoods. This brings us to the final engineering challenge. Even the most advanced physical barriers fail if they are deployed in the wrong sequence. Looking at this CDC sequence, we see that donning and doffing, the processes of putting on and taking off PPE, are strict, unalterable operational algorithms. The donning procedure is designed to build personal containment architecture from the inside out. You start by securing the largest surface area first, wrapping the gown securely to cover the torso and arms. Next, you establish the respiratory seal with the mask or respirator, followed by goggles for the eyes. Finally, gloves are put on last, pulled deliberately over the wrists of the isolation gown to create a seamless, overlapping seal. Donning requires precision to ensure a perfect seal, but it happens in a clean, safe state. The true danger of a biosafety failure occurs at the end of the procedure, during removal. Doffing is statistically the moment of highest risk. One wrong move can transfer concentrated pathogens directly to the skin or airways. The governing physical law is simple. You must treat the outside of your equipment as an active biohazard surface. Because hands are the most contaminated, the gloves come off first. You grasp the outside of the glove and peel it inside out. This traps the contaminated exterior surface harmlessly inside the material. Next, you remove the goggles or face shield. You never touch the front surface, which is the primary impact zone for splashes. Instead, you handle them purely by the clean headbands or earpieces. When removing the gown, you unfasten the ties and pull it carefully away from the neck and shoulders. By folding it inward and rolling it into a tight bundle, you trap any surface pathogens inside before discarding it. That leaves the final and most crucial step, the respirator. As noted here in the CDC guidelines, you do not remove your respiratory protection while still in the work area. The logic is absolute. Your airway must remain completely sealed until you have physically crossed the perimeter of the containment zone, closed the door behind you, and entered a clean atmosphere. The doffing sequence is an elegant subtraction of risk. You strip away the most heavily contaminated physical layers first, ensuring that your deepest biological vulnerability, your lungs, remains protected until the end. True laboratory biosafety cannot be bought off a shelf. It relies on an active, interlocking system, the physical security of the facility, the specialized engineering of personal protective equipment, and the relentless discipline of human protocols. In the high-stakes environment of clinical research, Safety protocols function as active engineering components, the final line of defense keeping the researcher and the biosphere safe.